And again, I wanted to finish up the little last part of naming here and discussion. That way, everybody will be on the same page. So last time we did start talking about naming, and again, these are the same notes that we've been working on there with the bonding, I believe. We talked about really two types of naming, and they both really revolved around ionic bonds, as we've talked about today as well. Again, an ionic bond is a metal and a non-metal together. And always when you have this, as we talked about, we will get that transfer of electrons from the metal to the non-metal, resulting in that cation that's positively charged and that anion that's negatively charged. And again, it's that opposites attract that holds that together. But in terms of naming, as we talked about, it is always the metal part. Whenever you combine a metal and a non-metal together, that is the most important part. And that metal in a type 1 compound, the metal comes from group 1, 2, or 3, or zinc, cadmium, or silver. And really what all these guys have in common is they have fixed charge, fixed positive charge. And whenever you have a type 1 compound, which again is a metal and a non-metal together, and as soon as you recognize that the metal is part of group 1, group 2, or group 3, or zinc, cadmium, or silver, or has a fixed charge like those guys, we just proceed straight to the naming. And again, we use the whole name of the metal, and we give the non-metal, we kind of drop the last part of the name. And again, that is the guy that gets the IDE after it. And again, for example, if we had KCl, K is really potassium with a +1 charge. Cl is chloride with a -1 charge. But most importantly here, that is a metal. That is a non-metal. And that metal is from group 1, which tells us it is going to be a type 1 compound, which means we just simply use the whole name there of the metal, which is potassium. Chlorine gets the IDE treatment at the end and becomes chloride. So type 1 guys, pretty straightforward. We have a metal that has a fixed charge. And if we see that, simply proceed to a whole name of the metal, IDE for the non-metal. Remember as well that if we look at this, which is a metal and a non-metal, we see that this guy is group 2 on the periodic table, telling us it is type 1. This would be calcium. And as we talked about last time, remember that although there are 2 of these here to balance out the charge, it has no effect on the name, and this would just be calcium chloride. Again, you should not use any type of prefixes with that. The reason there is a 2 again is because the cation is a calcium with a +2 charge, and each of the anions are actually chloride here with a -1 charge. So we do need 2 of them, which is why the 2 appears in the formula. But again, no prefix or no worries in terms of the name. We just simply call it chloride. And that's a little bit different than what happens when we get a type 2 compound. Type 2 compound, again, still your metal and non-metal. Again, out of the 2, it is still the metal that's most important. And the metal here comes from a transition metal, are just to the right on the periodic table underneath the staircase. So if you remember, underneath the staircase and outside of the transition metal region, in this area where we got things like lead, tin, antimony, bismuth. Obviously, I'm off the periodic table, but those guys are in this area. Those guys, what they all share in common is they actually have a variable charge, which means, for example, in certain situations, the same element can have a different positive charge. So something like copper, in some situations, copper will take on a +1 charge. In other situations, copper may take on a +2 charge. So the way we name these are pretty much identical to type 1. We still use the whole name of the metal. We still use the non-metal like we did before, drop the last part, put IDE at the end of it. The only difference is we actually do put a Roman numeral in between. And again, what the Roman numeral is the positive charge on the metal. So if you took one metal ion by itself, what the positive charge would be. Again, not how many of them that you have, which is a very common mistake that people make, but it is, again, if you just took the one metal by itself, what the positive charge would be. So speaking of copper, if we took something like CuO, this is copper, which is a transition metal, which automatically should tell you it is type 2. Automatically should tell you, perhaps I'm not sure what the charge is on it. But as we talked about at the end last time, the good news is you will always know what the charge is on what it is bound to. And that means the oxygen is group 6, which means it has a -2 charge. And remember, always when we put a positive guy and a negative guy together, we do want to end up with an overall charge of 0. So our copper here would have to be, in this case, a +2. +2 -2 gives us 0. And that means that the name here would be the whole name of the metal. We would do a Roman numeral 2, again, for the positive charge that we see on the metal. And again, our guy at the end there just gets the IDE treatment, and this would be copper 2 oxide. Same deal if we have multiples of something. So for example, if we had, move some things around, somewhere to the right, over here. We had CuO, for example. Here in this case, although it looks very similar, we still see that copper is a transition metal. And in this case, we do not know what copper is, but we do see we have 2 of them. So we actually have 2 in this case. We still only have one oxygen that has a -2 charge. In this particular case, the copper actually would carry a +1 charge. We would then name it copper Roman numeral 1, not 2, but 1, because the individual positive charge on the copper is +1. And again, the oxygen would become oxide. Even though we technically have 2 of those coppers, again, no prefix, has no effect on the actual name. Any questions on that stuff there we talked about, I think, last time during discussion? So then we will kind of continue on and finish up the last couple of things about naming. Here again is a table of some of the different guys in terms of their charges. Again, all these guys have variable charges, and we can see we do use the Roman numerals to indicate it. The one really weird one is mercury. And oddly, when you look at mercury with his Hg, 2+ versus Hg 2+. The one that actually has all the 2s is actually mercury 1, while the guy that has just 1 2 is the mercury 2 ion. And that's because really mercury 1 comes as what is referred to as a dimer. They come as basically 2 together, each has a +1 charge. So that's why it is a +2 on top, because each one has a +1 charge, and why there is a 2 on the bottom, because there's actually 2 individual mercury guys that are basically sandwiched together as to how they come. So that's kind of a weird one. Sometimes people wonder, like, how do I know which one's which? And usually that extra 2 that's there on the mercury 1 will still remain. So for example, if I did So this one, we see that extra 2 that's here. Again, the oxygen is -2, which means this guy is basically Hg2 2 plus or mercury 1. Here we do not see the 2 there, which tells us this is mercury. That also, again, this guy is a -2, a +2, no 2 on the bottom, which would be mercury 2. So that extra 2 that you see for mercury 1 does sort of hang around a lot of times in the actual formula. And that's really a one way you could kind of recognize it as mercury 1 versus, say, mercury 2. Good news is we don't come across it too much in here. So we sort of talked about this again, a reminder that it is always both in formula and also name. It is always the positive guy first, the cation, followed by the negative guy. And again, for our type 2, we do use a Roman numeral to indicate the charge. So let's take a look at this and again dissect what we should be doing. CO, which is a metal. So I see that's a metal. I see that is a non-metal. That automatically tells me it's ionic. When I look at cobalt on the periodic table, dead center, 27, I see that is a transition metal, which tells me it is a type 2. And that automatically should tell me I am not sure what the charge is on the cobalt. But again, if I look at what it is attached to, that is Cl, which is group 7. And group 7 has a -1 charge. And there are 3 of them. So again, -1, -2, -3 total, which means our cobalt here must be +3 to balance it out. And again, because this is a type 2, we would go cobalt Roman numeral 3 for the actual positive charge. And again, even though we have 3 of the chlorides, it is just chloride at the end. Any question on that name? If we look at this one, this is CuI. Cu again is copper, which is a metal. I is iodine, which is a non-metal. Again, that tells me it's ionic. I look at copper, I see it also in the middle of the periodic table there at 29. That tells me it is a type 2. And again, we need to figure out what the charge is. So copper, not sure. Iodine, which is group 7, has a -1 charge. So to balance it out here, the copper does need to be +1. And now we're ready to name it as copper Roman numeral 1, again, because that is the positive charge. And again, iodine becomes iodide, ID. Any question on that name? And lastly here, we look at this, which is tin, which is a metal. We look at Br, which is bromine, which is a non-metal. Again, tells us it's ionic. We take a look at tin, and when we look at tin on the periodic table, although it is technically not a member of the transition metal, it is below the staircase in that area where I described that has multiple or variable charges. So that tells us that it is a type 2. And same approach here. We have 110 that has a positive charge. We have 4 of the BRs. We know that BR is group 7, which means 1, -1, -1, -1, and -1. That is a grand total of -4. That means the positive charge on the 110 has to be +4 to balance it out. And that then yields me a name of the whole name of 10, Roman numeral 4, again, because it's +4 here. And even though we have 4 of the bromines here, it is just named with the IDE at the end of it. And this would be 10 Roman numeral 4 bromide. Oops. Any questions on any of those names there? Okay, so again, that's a little review there of type 2 that we talked about last time, I believe. Let us then get into maybe type 3 here. And this is, again, a reminder of what we just talked about. Those that do not require a Roman numeral, which are type 1 guys, which are these guys. Those are our group 1, 2, and 3, zinc, cadmium, and silver. A reminder that zinc always is a +2, cadmium is always a +2, and silver is always a +1. Again, our transition metals do need those Roman numerals, as we just saw, except for obviously these three. Those are really small. Just gonna skip those because I cannot see them, so we'll skip those guys here. All right. Type 1 and type 2, again, it's kind of a decision tree as to which way to go. And again, we've talked about that. So now we're going to talk about type 3 compounds, and type 3 compounds are different. Type 3 compounds are actually two nonmetals. And as we've been talking about with the bonding as well, that should tell you that these are covalently bonded together, which means we have some sharing of electrons. And most of the time when people start to name things or try to name things, they always want to use those prefixes on things, you know, like, hey, there's 2 chlorines, so dichloride and stuff like that. This is actually the one and only place that you should use prefixes. So with type 3, non-metal naming, this is actually the appropriate place to use prefixes. Things like mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa 6, hepta is 7, octa is 8, nona is 9, and deca is 10. So we do use these prefixes. Personally speaking, I think that type 3 are definitely the easiest of all naming. But with that being said, it is also the one that people frankly screw up most because they try to do all kinds of weird things they shouldn't do. They try to balance things and do all kinds of weird things. So although it is relatively sort of the easiest in terms of naming, unfortunately, it really is the one that people kind of mess up on a lot. It's not this, that's not the correct number, so I'll scratch it out of your table there. You do have a table in your book, but it's not the correct number there. So how do we go about naming these? Well, frankly, we use the whole name of the first element that's there. So we do use the whole name of the first element, and we do use the appropriate prefix with that. And then the second element gets really the non-metal name with the IDE at the end of it, and also the appropriate prefix in front of it. So prefix, whole name of the first element, prefix, IDE name of the non-metal here. Now, there are a couple of things that are important. First off, we never use mono on the first name. So no mono on first name. But it is okay on the second. So the second name, it's all good. You could use it, but we definitely don't use it on the first name. The other thing that happens, as we will see here, is sometimes when you take a prefix and the first letter of the next name, you get a couple of vowels that back up to each other. So for example, if I had one oxygen, I might write mono for one and oxide for the other. I now get 2 oxygens here, and it would be called monooxide, and we don't call it that. So typically speaking, 2 O's, we get rid of the O in the prefix, and the correct sort of spelling and name would be monoxide here rather than monooxide. Also happens sometimes with tetra and oxygen, same idea. Tetraoxide, we have an A and an O together. So typically speaking, we kill the vowel that's on the prefix here, and we call it tetroxide here. Again, dropping the A. So sometimes we get a couple of vowels that back up to each other and we sort of get rid of those. I will say that the one vowel back to back that seems okay. It's like, for example, diiodine, 2 I's in a row. Seems to be okay. But typically an A and an O, we drop the A of the prefix. 2 O's that back up to each other, we also drop the O of the prefix. Any questions on that there? And here's a table, again, similar to one that you should have in your book there. And our di or tri or tetra. And again, those couple of things, no mono on the first one, but okay on the second. And again, just kind of correcting, some of these situations where we might get a and an O that comes out back to back, where we drop the A of the prefix. And that's sort of what this slide is talking about. Now, a reminder that there are certain things that really do have sort of common names, and these are the names that we typically use when we're dealing with those. Most popular one is water, H2O. It is not dihydrogen monoxide. Nobody wants a refreshing glass of dihydrogen monoxide. People much rather have a refreshing glass of water. So if you see H2O, it's not a trick question. It is water, and that is how you should refer to it. NH3 is ammonia. And one other one that sort of adds to this list, but I think we maybe saw earlier, is CH4. We definitely will see this guy again. That is the simplest organic molecule you could have, and that is what is known as methane. So methane here, simplest organic molecule you could have. And those three guys for us are typically the ones that we do with our common names. So let's take a look at a couple of these here to kind of see what we got going on. So again, here, this is what we want to approach it, or how we want to approach it. We want to look at this, and I see I, which is iodine, that's a nonmetal. I see O, which is oxygen, which is a nonmetal. That is 2 nonmetals together. That tells me this is a type 3, which tells me I'm very happy, because frankly, I don't have to figure out anything in terms of charges or anything like that. I simply just need to say what is there. Prefix for 2 is di. Prefix for 7 is hepta. And again, we use the whole name of the first element. So this would be diiodine. Again, the 2 I's okay here. The second guy will get the IDE treatment, and that would be hept oxide. Here I'm dropping the A because the next letter is O, so A and O would be a bad back-to-back, and we get diiodine heptoxide. Any question on that one? Here we look at it, we see carbon, which is a nonmetal. We see oxygen, which is a nonmetal. Again, that tells us 2 nonmetals. That tells us type 3. That tells us prefixes is what we need. So here we have 1 carbon, 1 is mono. We have 2 oxygens, 2 is di. So starting with the first name, remember we do not use mono on the first name. So we would just use the whole element name there, which would be carbon. Second one would be di, and then oxygen becomes oxide, dioxide here. And that would be carbon dioxide in this particular case. Any questions on that one? Same idea here. We see P, which is phosphorus, which is a nonmetal. We see Cl, which is chlorine, which is the nonmetal. Again, going through our checklist, 2 nonmetals tells me it's type 3. Type 3 tells me this is the appropriate place to use a prefix. Again, we do see only 1 phosphorus, which means mono's in play. We do see 3 of the Cl's, which means tri. Again, because the phosphorus is the first element here, we will not use the mono on that name. We'll just use the whole name here. The second guy gets the IDE treatment along with the prefix. This would be trichloride, phosphorus trichloride. Any questions on those naming there? Okay, why don't you try a few here just to make sure. Let's see here. Let's do. Why don't you give the name for N2O5 for CCl4? Why don't you give the formula for sulfur trioxide? Oops, as I run off the screen, let's try that again. Sulfur trioxide. Why don't you give the formula for dioxygen hexasulfide? All right, so proper name here and proper formula here. Take a couple of minutes and see what you come up with. Again, really these should take you the quickest. Again, you don't want to overthink it here. First off, we just want to do our identification. We got nitrogen, which is a nonmetal. We got oxygen, which is a nonmetal. Again, telling us we got two nonmetals, telling us that we are dealing with a type 3 compound and prefixes. At that point, you should be really happy not to figure out any balancing or charges. Simply what's there. We see two nitrogens, so prefix for two is di. We use the whole name of the first element, which would be dinitrogen. Second guy's got 5. Prefix for 5 is penta. The second element gets the IDE. So we just want to watch our vowels here and drop the A off of the prefix. And we get dinitrogen pentoxide. Any questions on that one? Looking here, following the same approach, we see C, which is carbon, which is a nonmetal. We see Cl, which is chlorine, which is a nonmetal. Again, running through our checklist here, nonmetals, type 3, and prefixes. I see only one carbon, which the prefix would be mono, but again, we do not use that on the first name. So we just use the whole name of the element. We see 4, which is tetra. Second element gets the IDE at the end of it, and that is carbon tetrachloride. Any questions on that name? The easiest, I think, out of all of them is actually doing these guys, going from the name to the formula here. When I see sulfur trioxide, the tri is a prefix, which tells me I'm type 3, so I just need to write what it says. Sulfur with no prefix on the first one means I have 1. Tri is 3, oxide is oxygen. SO3 would be my formula in that case. Again, nothing to balance in this case, simply just what it says. Second one, di and hexa tells me I got some prefixes in type 3. Di is 2, oxygen is O. Hexa is 6, sulfide is S. And there we go. And that made up thing O2S6 would be it. Any questions on type 3 naming? Covalent bonding, molecular compounds, the appropriate place to use prefixes. Any questions on that? All right, then let's talk about the last type of naming here after we look at the review of the 3 different types we talked about up to here. Type 1, again, are metal, non-metal, ionic. Metal important, group 1, 2, 3, zinc, cadmium, or silver. Whole name of metal, non-metal, IDE, no Roman numerals, no prefixes. Type 2, metal, non-metal, ionic. Metal is a transition metal with a variable charge. Whole name of metal, Roman numeral for the charge on the metal. Non-metal, IDE, again, no prefixes. Type 3, non-metal, sharing electrons, covalently bonded. This is where we use prefixes, prefix and whole name of the first element, prefix and IDE of the second element. Do not use mono on the first name, okay on the second name. Any questions on the differences there? And a little decision tree in case you want to look at it later. So the last type of name we're going to talk about are guys that basically contain polyatomic ions. And polyatomic ions are basically groups of nonmetals that are held together by sharing of electrons, but actually have an overall charge, which makes them ions. And if we were to take this guy and break it up right here, this would be NH4 plus. That one nitrogen, 4 hydrogens are all sharing electrons and move around as one unit, has a +1 charge, never breaks apart individually. It is what we drew earlier today. It is this guy. They are sharing electrons. They are bonded together. They move as one unit. That is another polyatomic ion on this side. That is 1 nitrogen and 3 oxygens with a -1 charge. Same deal. That nitrogen and 3 oxygens all move around as one unit, has a -1 charge. It is a Lewis structure that looks like this. All those guys are sharing electrons and held together, so they move around as a whole unit. Also, why when we put it together, it's a +1 and -1, which means we just need one of each of those guys to put our formula together. Just like we talked about earlier, positive, negative needs to equal 0 when you put it together. This is what is referred to as the ammonium ion. This is the nitrate ion. And if we were to name this guy, we simply just use the names and putting it together for NH4NO3. This would be ammonium nitrate. Basically, just put both names together. Now, there is a list of these polyatomic ions. Here's one list. And unfortunately, the best way is you got to memorize them. And the way that you can memorize them there are things that are related to each other. So for example, that is NO3 minus and NO2 minus. The only difference between these two is the number of oxygens. One is nitrate, one is nitrite. The one with the most oxygens in a group of 2 will end in 8. The one with the least number of oxygens in a group of 2 will end in ite. So that's like the most oxygen, the least oxygen. For example, if we look at SO4 2 minus and SO3 2 minus, SO4 has 4 oxygens, SO3 has 3 oxygens. They both have the same -2 charge. The one with the most oxygens ends in 8, sulfate. The one with the least oxygens ends in ite. So groups of 2, the one that ends in the most oxygen or has the most oxygens ends in 8. The one with the least ends in ite. There are also groups of 4 that are related to each other. Every single one of these guys have a -1 charge. The only difference is the top guy has 4 oxygens, 3 oxygens, 2 oxygens, and 1 oxygen. So if we kind of separate it right about there, everybody above here has the most oxygens, and they both end in 8, like chlorate and chlorate. But in a group of 4, the one with the most oxygens will also begin with per. So that is perchlorate, chlorate. If we look at the bottom 2 here, they have the least number of oxygens. They both end in ite, chlorite, and chlorite. But the guy with the least number of oxygen in a group of 4 will start with hypochlorite. So that is perchlorate, chlorate, chlorite, and hypochlorite. You could also swap out that halogen for any of the halogens like this. So instead of Cl being there, I put Br in there. Instead of chlorate like it is here, it becomes bromate, because that's bromine. Other common things that we see is we take carbonate like this guy and we put a H plus on it. And we get HCO3 minus. We basically put a hydrogen, that is what is referred to as hydrogen carbonate. And sometimes instead of hydrogen, people will use the word bi, like bicarbonate instead of hydrogen carbonate. We also see that down here with hydrogen sulfite or hydrogen sulfate, bisulfate, bisulfite. So sometimes instead of saying hydrogen, like we put in front of it, people will use the terminology of bi in front of it for that. Now, sometimes the best way to do this is sometimes people will remember all of the eights and know that the ites are basically one oxygen less, or vice versa, learn all the ites and all the eights would be one more oxygen. Or if people would learn them individually, that's a good way to do it. Learn them all and just know one less, it would be all the ites. Now, in terms of polyatomic ions, this guy right here, which is NH4 plus, is probably one of the few positive polyatomic ions we'll come across. So for the most part, what we'll see is the polyatomic ions will really be hooked up with metals. And before we get to that, there are some polyatomic ions that actually end in IDE, like OH minus is hydroxide, CN minus is cyanide, but a vast majority of our polyatomic ions will end in ATE or ITE. And as I mentioned just a second ago, typically speaking, we'll look at this chart maybe. There you go. Basically kind of the same guys, just a different chart. They typically will be hooked up with a metal, which means we fall back to our type 1, our type 2 rules. And again, the difference here is fixed charge on the metal, no Roman numerals, variable charge on the metal. We need Roman numerals. So we do follow the same thing. So for example, if I put sodium with the nitrate, we would break it up here. This is a sodium ion. This is a nitrate ion, which is right here. And because we have a metal involved, again, it is the most important thing. And we see that sodium is a type 1 metal, which means we would simply name it very much like type 1, sodium, and we would just use the whole name of the polyatomic ion, which would be nitrate. Now, if we put that same sodium with a type 2 metal like iron, this tells us the metal is a type 2, which means it could have a variable charge. This is nitrate, and there's actually 2 of them, which means the overall charge here on the negative side is -2. That means that the iron here would be +2. And much like in type 2, this would be iron Roman numeral 2. And just like we did with type 1 or type 2, even though there's 2 of these guys, it has no effect on the name. We just use the whole name of the polyatomic ion, which would be nitrate. Also really important is whenever you have more than one polyatomic ion, you do need to put those parentheses around it and the number on the outside there as to how many you have, because if you write the formula like this, that would imply that you have 32 oxygens, which is really not what you have. So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number on the bottom. So if we look at a couple more examples here, we have calcium hydroxide, and we want to write the formula. We would follow the same basic thing. This is calcium, which is group 2. It has a +2 charge. This is hydroxide, which was on this table somewhere. Where did I see it? Should be there at the very bottom. There it is. which is OH minus. When we put these together, we want to make sure that we do end up with no charge. So we have +2 on the left, -1 on the right, as this whole thing is -1, which means we actually need one more of those guys. And that would give us +2 and -2. So again here, calcium, we do need the parentheses because we have more than one polyatomic ion and the number on the bottom there, which would be calcium hydroxide. You do not need parentheses if you only have one polyatomic ion, but you do need them if you have more than one. Question on that there. So if I had NH4 2s, and if I had copper 2 phosphate, again here, we would look at this and see that's NH4 plus, which is our ammonium. And that is S, which is sulfide. So basically what we have here is 2 of these guys, +1, +2, to balance out our -2 charge that comes from the sulfur. And we would use, again, even though there's 2 of them, we would just use the whole name of the polyatomic ion. So this would be ammonium, and the S would become sulfide, IDE at the end of it, as is from the periodic table. If we had a name, we see copper Roman numeral 2 tells us the copper has a +2 charge. Phosphate from the list here is PO4 3-. So ultimately we're putting together a +2 and a -3. Common number there is 6. To get our copper to 6, we actually need 3 of them, which would be this. That basically tells us we have 3 of these guys, +2, +4, +6. To get our phosphate to 6, we actually only need 2 of them, which means we can just put a parentheses because we do have more than one, and we do need to put a 2 there. That 2 indicates that we have 2 of these guys. -3 and -3 is -6. The 3 here indicates we have 3 of these guys, +2, +4, and +6. So for the most part, our polyatomic ions will pretty much be hooked up with metals, and we follow really the type 1 and type 2 naming process. And again, it's the metal, if it's type 1, does not need a Roman numeral. And if the metal is a type 2, then obviously you do need the Roman numeral. Any questions on polyatomic ions here? So again, unfortunately, the best way is, unfortunately, you do have to memorize these, both formula and charge, so you could put things together correctly, and also the name of them so you can name things correctly. And again, you want to look for these patterns. And again, in a group of 4, like we were talking about there, that's where we see the per and the hypo happen. And again, in a group of 2, we do have the 8 and the ite that happens when we look at those patterns. And again, sometimes we do put the hydrogen in there. Any questions on naming polyatomic ions? That should wrap up